So I'll solve these questions of midterm. So I'll also write some parts of the question. Okay. So Green's function. So this is objective part. Green's function for 2D Poisson equation. Okay. So Poisson equation is L square phi is rho of x. So it's a vector, it's a 2D vector. Okay. So what will be the Green's function? So Laplacian g of x equal to delta x. So given that the source is at the origin, so x prime is 0. So we can do it in real Fourier space as well, as real space as well, but let's do in Fourier, the way we did in our lectures. So Fourier space, this is going to be k squared. So so minus k squared. Well, I think minus k squared. Laplacian gives you x equal to 1. Delta function, if integral is integral delta x is, so it's a volume. Okay, so this is a volume integral. So g of k, sorry, this is g of k. So g of k is minus 1 over k squared. So this derivation has been done, but I am repeating it just for revision. So once I have, so it is isotropic. The potential, this is a potential, right, for electric field for a point charge. So that's the meaning of Green's function. If you have a point charge, well, it's not a point charge, it's point in 2D is a line charge. So it's really the potential due to a line charge sitting at the center. Okay, there is a bit of notation change. In electrostatics, there is a minus sign here. But since we are talking about the Green's function, we keep plus sign there. Okay. So now I just want to go to g of x by Fourier transform vector integral dk by 2 pi squared e to the power I k dot r by e to the I k dot r, so by k squared. So this Fourier transform of 1 by k squared minus sign. Okay, so we can do this stuff. So the answer is in terms of Bessel function. Okay, but so in fact the answer is in terms of j dot Bessel function, but it turns out we do all that algebra. We know from the answer that it is connected to log of r. Is isotropic. So I want you to write like log of r, there is a prefactor in front. Okay, so answer is log of r, which is connected to the Bessel function. So this derivation, I think I didn't mention in the class, but you know from electrostatics, no, that the potential is log of r for a line charge. Now let's determine this prefactor. So the integral is not so straightforward, but we can choose my r direction in that direction. K is integrated, this angle is theta, phi. So this is going to be e to the power I k r cos phi by k squared dk d phi. Okay, so this is a Bessel function, but if you do all that algebra, you'll get log r. Now, so it is not function of angle, it's isotropic, right? It doesn't depend on angle. Now, how do I find the prefactor? Okay, of course, if you do the integral, then you'll get the prefactor, but we can do it another way, now which I didn't do in the class, but I'm doing it now. So the Laplacian in real space. This is another, so you can do this in real space as well. So what is Laplacian in real space in 2D? So 1 over R, well, you call it 1 over rho, d rho, rho dg by dr, d rho equal to delta function. Rho is a distance. Now, there is another factor. Okay, so since I am doing some math, so there is another term. This is the radial part. What about the angle part? The angular part as well, no, in 2D. So that is d squared g, d squared phi squared by rho squared. But this term is 0. Why this term is 0? Because g is independent of phi, isotropy. So that is why it is getting contribution from m equal to 0 mode, the azimuthal symmetry. So, so in general, this Green's function is function of rho and phi, and phi is that angle. So this is my angle phi, rho, and my Green's function is function of phi as well. But for this problem, because of azimuthal symmetry, the phi part is gone. So this part is 0. Okay, now, I mean, if you are interested, you should look at your mathematical physics notes or book. This gives you m squared. Okay, if you recall, so in general, so this Bessel function is written as j m rho, j from rho and e to the power I m phi, and this m is coming from this m, azimuthal. So sine phi, sine 2 phi, sine 3 phi, like that. Okay, anyway, we will not get into that part. So for us, it is straightforward. This m is 0, so this is gone, and this is 0. That's how it comes. Okay, anyway, so this is my, I need to solve this. So what should be g? So g I know is log of r. Let's call this prefactor a. So what is the derivative of log r? Log rho. Okay, so let's call it log rho. So what is the derivative of log rho? Is 1 by rho. So rho 1 by rho a d by d rho 1 by rho. So what is this? D by rho of a constant is 0. So this is 0 for all rho's except this derivation is not valid for which rho? Rho equal to 0. Rho equal to 0, there is singularity. So I can't take a derivative at the singularity. So how do I solve it for rho equal to 0? So for rho equal to 0, we need to do the Gauss theorem. So you make a small circle, okay, and this distance is rho, but rho is tiny. So I want to integrate both the sides. So I think it's best to just go to your electrodynamics derivation. So this Laplacian of g will be, g is a scalar. Divergence of grad g equal to delta of rho. It's a 2D stuff, okay? That delta squared of rho. Let's call it delta squared of x. 2D delta function. So apply the Gauss's theorem. Yes.
You are first writing rho like density, and again you are using rho as a variable.
Okay. So let's call it charge. Okay, so this charge. Okay, you're right. So rho is a radius for me from the center. All right. So apply Gauss's theorem. So that will give me integrate both sides. Okay, over this area. So integrate over both sides over this area. What will I get? The volume integral is 1 because the delta is inside, but the left hand side will be, so I am integrating both sides, okay, over volume. So left hand side is grad G dot area ds. Gauss theorem, no? So volume integral of divergence equal to the the vector field dot ds over the whole area. This is a closed one. So what is this? This is the closed volume. Okay, this is. So now I know this. It is of this form. So gradient of this is what? A by rho. If I take the gradient, I'll get A by rho, and direction is rho cap.
Outward of the
Outward.
boundary.
Outward. So it is in that direction. The electric field is in that direction. Rho cap. And what is ds? Area integral?
This is R, rho times
Rho d rho d phi. This is my left side.
integrate that not.
And this one
Yes, so you integrate with the volume.
is volume. So dx is volume. So 2D volume is so this is no, you're right. Sorry. You're right. So 2D volume. So this will be the area will be a dl. The area will be this one area. So this is not correct. Sorry, yeah, that you're right. You're totally right. So I need to integrate like that. My area is that. That's my surface. So you can think of a cylinder. Thank you. That is very correct. So area is well. By the way, it's still called ds, but area is this element. This element is the area. And what is that element?
Rho
Is outward again rho d phi. No dr. Rho d phi, right? This is the rho d phi, and it's still pointing outward. Rho cap. So this is equal to 1. Okay? So this rho cancels. Rho dot this one is 1. A d phi gives you 2 pi is 1. So A is equal to 1 rho. So my exact Green's function is A is 1 over 2 pi. Okay, so that's Green's. But even if you don't write 2 pi, it's okay. I'll give the full marks. But okay, we can get this 2 pi from this integral, but it is complicated. This integral is definitely not easy. It's function of Bessel function. But so we can solve using this. That's problem 1. Problem 2. So it was Fourier transform of theta x 1D. So it's a theta x is a step function. The step function is the x-axis is theta x. So for x greater than 0 it is 1 and below it is 0. Okay, so I've done in the class, in fact it's straightforward. Integral theta x e power I kx dx. This is my Fourier transform. Okay, so it goes from minus infinity to plus infinity. But this part is 0. So you can simply do from 0 to infinity. Okay, but it turns out this integral will be not convergent, right? Because e to sine kx or cos kx dx is oscillating all the time. So you put a small separation term. What is small separation term? Minus epsilon x. Do that. Okay. So epsilon is positive, but a small quantity. So epsilon tends to 0. But now it is suppressed. At infinity, this function will go to 0. So this is the finite answer. And this you can easily do this integral. I divided by k plus ix. Okay, so these are Fourier transform. So I will not go to, well, this integral I will leave it for you. The time dependent Green's function, time dependent Green function for Schrodinger equation, d-dimensional Schrodinger equation. Now we want to only find the dimension. So time dependent, okay, time dependent. So time dependent Green's function. So normally it is defined like this. So it's time dependent, so write down the operator minus Laplacian, which is the Hamiltonian. So that's Hamiltonian is a free particle. I did write free particle or source at the origin, but this for the free particle, okay, so I did not write it, but it's for free particle. Laplacian G of R equal to delta R. Source is the origin. And this function of time as well, huh? So RT. And the notation is, so this is there's a time as well, delta t. It is just starting at t equal to 0, the source, and IH bar. So it is written, IH bar is kept here for dimensional reasons. But if you didn't do this, that's also okay, but it is written like this, IH bar. Now, what is the dimension of G? In fact, you can see easily from here. So compare this term with that term. Dimensionally, this should match. Left dimension, right dimension. So what is the dimension of the left hand side? This term only, okay? IH bar dt of G, dimensional, equal to delta R, delta T, IH bar. So IH bar cancels. What is the dimension of delta? 1 by time. So 1 by time will cancel with this. So G has dimension of delta R, which is for d dimension L by d, L to the power d. Right? In 3D it is L cubed, 2D is L squared. So that's the dimension in d dimensions. So I should write d of dim of d. The fourth one was relativistic invariant quantity using E from vector. So E is energy, P is a momentum. So this is E squared minus P squared. Assuming C equal to 1. The speed of light is 1. But if you want to keep C, then this P squared, C squared. Okay, so that's our invariant quantity. Okay. All right. So massless relativistic field Lagrangian. Okay, so for real field, the field is real, then Lagrangian density, okay, Lagrangian density is del mu phi. Massless is 0, so there's a term which is m squared phi squared. So this term goes away. So this goes away. And we put half there actually. But I won't mind if you don't put half, it's okay. This for real, but if you want complex, then you just put a star. Okay, so either way is fine. I mean, if you write the complex or real, full marks. So in field theory, conservation of energy is related to which symmetry of the Lagrangian? So conservation of energy symmetry is prime translation. That means if you take a system, full system, do the experiment today or do it tomorrow, you will expect the same result. Okay, so but of course you have to keep the same system. So for example, on the earth, if I do an experiment today in our lab, physics lab, I'll get some number, but tomorrow I expect to get the same number. However, do you expect after, let's say, 1 million years, if I do the experiment, will I get the same number? No, the earth would have changed, no? Earth would have maybe lost mass or gained mass. So if you take the same earth of today and translate 1 million years later, so you have to take the full system, not only part of the system. So that's the important thing. Lagrangian of the full system is invariant under time translation. Now fermion. So fermionic operators. So A dagger P1, A dagger P2 equal to lambda, A dagger P2, A dagger P1. So what's the value of lambda? -1. So it anti-commutes, not commutes. So if I create a particle P2 then P1, so you get a wave function P2 P1 which is antisymmetric to P1 P2. Okay? So lambda A is -1. And for bosons, wave function is symmetric, so it is +1. Now write down the commutation relationship for fermions in real space. So they anti-commute, okay? So that's anti-commutation. So if I have psi of x operator, psi dagger of y, this is a delta function, not square bracket, but so adding, so you have to add this. That is delta x minus y. Okay, so if it has component, then you have to put delta of that component. So for electrons, this psi field has component, spin up, spin down, right? So that but let's ignore comp. If you write with component, that's also fine. So if your component A and B, then it is delta AB. And so this is psi creation and destruction operator. That anti-commute, there is a delta function, delta. However, if I put creation in I tell you why. So this is equal to 0. But it's anti-commutation. So it is in fact connected to this. So created y, then created x, and vice versa. So you have to add them and it becomes 0 because the wave function is antisymmetric. And same thing for a destruction operator. So this is. So next question was field operator for complex scalar field. So psi of x equal to integral so some people if you wrote only cubic that's also okay. For this for relativistic, for non-relativistic this is cube. But you need to write the time part, huh? So time part is important. So AP e to the power minus I p dot x. So this is the four momentum. So it has time as well as space. It is minus I e t minus p vector dot x plus b dagger p. So it's a antiparticle which is e p dot x. So well, if you wrote only a, I mean still give marks, but it's antiparticle, not the same particle. Okay, so it's antiparticle. For complex it is antiparticle. For if it is real, then it is the same particle. Yeah.
Factor of 1 over square root of
Yeah. So that factor, you're right. EP. 2 EP, 2 EP. But I will ignore that if you not written it. Yeah.
we include factor of that 2 in this is 3 momentum.
Oh yeah, you're right. 312 is it 312. Okay, but I'm interested in this part only, okay? Because I did not cover this in the class. Normalization, I did not do it. So I will let go the normalization. Okay, now for wave function, which is psi of x is n to the power I p dot x minus e t. If this is a wave function, then Noether current first component. So I am interested in J0. And the formula for J0 is this done in the class, phi star of x. This is a d by dt, okay? So d by dt of phi x minus phi. So plug that in, and it happens to be 2 mod n squared e. Okay, so this current is proportional to the energy, first component, for this wave function. Okay, the next one is slightly tricky. Well, it's not tricky. This one is not tricky. The other one is more tricky. So for bosons, you need to evaluate A dagger 1, A1. So these are operators. A3, A2 dagger, A2, A3 dagger. 1, 1. So there are 3 Fock states, or 3 states in three state in the Fock space. So this corresponds to 1, 2, and 3. So there are 0 particle with momentum 3, 1 particle with momentum 2, and 1 particle with momentum 1. So this is our reference book, gifted amateur book. So we need to compute this for bosons. Now bosons, so if you recall the if they are same particle, then they do not commute. So for bosons A dagger P, AP, is equal to 1. Okay. E or A dagger, I forgot. A dagger. Okay. A dagger. So that is 1. Okay. But otherwise, if it is Q, then it will commute. You can shift around if they are not the same momentum. So we can shift around without any problem because they commute. So it's right. So let's look at, for example, this one. So this is in the particle number. No, A1 dagger, A1 is particle number, which is great. But A3 and A3 dagger are not together. So what do I want? I know that A dagger 1 A1 acting on n particle in that state, that would give me n. So I want to use this relation. So this is in that form, but here this is also the nice form, but this one is not in the same form, right? So what should I do? So I can push it to the right. So I can take these two and switch. If I switch, what happens? So they commute, so no problem, I can switch them. So please remember A3, A2 dagger is 0. Okay, there are two different momentum. So A3, A2 dagger is same as A2 dagger, A3. So that's switchable. So I can switch here, then take A3 and switch from there as well. Keep moving it, it doesn't matter. You can move bosons in this table wherever you like. So I'm going to bring A3 here. So that means if I bring it there, because shifting doesn't change any sign. So that is that A2 dagger, A2, A3, A3 dagger, 1, 1, 0. Now what does A1 dagger, A1 do to 1? Just gives you a number of particle, which is 1. So this is just give me 1. Okay, no problem. What about this? That's also 1. So these two are gone, and we are left with A3, A3 dagger. Whether I can shift it around. So if you want, you got to shift it that first. You take the whole block and shift. Doesn't matter. Then shift this. So bosons, that's a nice part. You can shift it around. And what is this object? So is a commutation, this one relation. So 1 minus A3 dagger, A3. I need to do that. So this is a number operator. So 1, 1, 0 coming from here. So what is this one? A3 dagger, A3 acting on this? Plus. Thank you. 1 plus. So A3 acting on 0 is 0. So this acting on this state is 0, and but 1 acting on that is same. So that's 1, 1, 0. Okay. So it's just working with these operators. Yes. Now let's look at the next problem. So these are fermion now. Okay. So fermion is a bit tricky. So C1 dagger, C1, C3, C2 dagger, C2, C3 dagger. Now they're fermion. So a fermion anti-commutator. So we replace this by anti-commutator. Or C1 and C3 anti-commute. So if I change the order, then I have to do I get a minus sign. Why? So just focus on, let's say this one, C1, C3. This is equal to 0. That means C1, C3 plus C3, C1 is 0. So if I change the order, then I need to get a minus sign. Okay. So I like to do something similar. Bring the number operator. Okay. bring to that form. So the idea is to bring C3 to the left. Bring C3 to the left. So this switches here, 1. So I get C3, C1, then do another switch. C1, so switch. So C3 coming to the left, what will happen? C1 dagger, C1, C2 dagger, C2, C3 dagger. So will it be plus sign or minus sign? Huh? No. This switch was 1 minus, and then I switch again. So minus minus becomes plus. 2 minus. 2 shift means 1. Okay? Now I want to shift this one. So it has to cross this, 4 of them. Okay, so keep shifting to the left. So 4 will be again plus 1. So if I do this stuff, C3, C3 dagger, C1 dagger, C1, C2 dagger, C2. Now it is in a nice form. So what about C2 dagger, C2? So this is 1 here, right? So the one particle with momentum 2. So this will destroy and create. So it remains unchanged. Right? This one is a number operator. C2 dagger, C2 is a number operator even for fermion. So it could be either 1 or 0. So by the way, for fermion this cannot be greater than 1. So this acting on this gives you 1. This one acting on this gives you 1. So we are left with C3, C3 dagger, 1, 1, 0. Now, so this will act on 0, this will act on 0. Again I want C3 dagger to come to the left. Right? So what will happen? C3 coming to the left. So this is a anti-commutation. So C3, C3 equal to 1. So what will I get here? C3, C3 dagger plus C3 dagger, C3 equal to 1. It is 1 minus C3 dagger, C3, 1, 1, 0. Okay. So what does it do? C3 dagger acting on 0? 0 again. Because C3 is so vacuum. C3 acting on vacuum. It gives you 0. So this again gives you 0. So it gets 1, 1, 0. No sign change. Okay. So fermion you have to be just put a minus sign if you do any flip. With the different particles, different momentum particles. Different momentum particles, okay, not different particles. Now the next problem is something very similar. So this one is, in fact, is there from the book. C1 dagger, C3, C2 dagger, C1. C3 dagger, C2, 1, 1. Okay, so we can apply very similar ideas, but here the last step. So there is a sign change. Okay, if you want, I can do it in steps. So I am bringing C3 and C3 dagger. So A1, this one goes to the right. Okay. So I will leave. So let's do it. Since we are doing it for the first time. So this one to the right, another right. So two right. C3, C2 dagger, C1 dagger, C1, C3 dagger, C2. Okay. This is same sign because C1 hopped twice. So now I want to bring C3 to the left. 1, 2, 3. So minus. So C3, C3 dagger, C2 dagger, C1 dagger, C1, C2 dagger, minus. Now I can take this to the right. So 2 hops means plus 1. C3 dagger, C2 dagger, sorry, C1 dagger. So I'm taking to the right. So C1 dagger, C1, C2 dagger, C2. So this is number number operator acting on 1. Number operator acting on 1 is 1. But this one acting on 0, in fact we worked it out. This one gives you same, right? This is worked out here, but the minus sign in front. So overall it is minus 1. The minus sign. Okay, so this is what condensed matter people, especially condensed matter phases. So these are hopping of particles, okay, is hopping on the lattice. So, it's not lattice hopping, it's a momentum hopping right now. But you can apply similar idea in lattice as well, in real space. So real space hopping also, the commutation relation is, where did I erased it. So commutation relation also has a minus sign. So they call, what model is called? Tight binding model, okay. So tight binding model is hop. And in the last problem in the series was the Green's function. Well, no, you need to evaluate this. So let's evaluate integral dk by 2 pi square e to ik dot r is in 3D. Okay, so this I have done in the class. Okay, so just to give you a sketch, so this is summed over all k's, and it's isotropic. Okay, it doesn't depend on angle for r. So in fact, this one we already know, it's a Poisson equation. Without m equal to 0 is Poisson equation. So what is the answer for 3D? 1 over r. With m squared there is a bit of change. So the idea is to choose this k vector and this r vector along z direction, and this angle is theta. So you write this as dk k squared d cos theta d phi 2 pi squared, and this written as e to power I k r cos theta. So d phi integral gives you 2 pi. It's not a function of pi. So this is gone. Okay. Now d cos theta. So don't do the theta integral. Okay. So use cos theta as z or some other variable s. So ds I k r s. So that gives you sin k r. Right? The limit for cos theta is -1 to 1. So in fact, you write as e to the power I k r minus e to the power minus I k r by k r. This is coming from theta integral. And my dk is going from 0 to infinity. And there is a k coming from k squared dk. No, so dk is already there. So this cancels 1k. Now this function, I want to extend this integral from minus infinity to plus infinity. So what should I do? So in fact, when I change sign to k, this becomes minus k and this becomes plus k. So in fact, this is very easy to show that it is dk 1 over r k e to the power I k r. we forgot this k square plus m square. Okay, so this is 1D integral now, and we can do using complex integration. So where are the poles? Im and minus Im here and here. Now you close from the top. Why? Because this should vanish. So I want zero contribution from this. So if you do all that algebra right, you get e power minus mr by r, and there's a factor 2. Okay, there's a factor 2 comes. So that's the answer. If you don't get right factor 2, it's okay, but you need to have this. Okay, so this is the device shielding. So for finite mass, there is a device shielding. The potential is suppressed. Okay, so any questions? I can take a slight break.
Why you drop that out? It is done one time.
This was done many times in the class. So this part imaginary k is, so k will be written as k real plus I k imaginary. So this is a complex integral. Okay, I go from real line to complex plane. So ik, if I multiply here, well, I plug it in ik imaginary. So I times ik imaginary times r. So it's minus ik imaginary, and k imaginary is large. So this is that Jordan lemma. Okay, Jordan lemma was done. So you choose upper or lower depending on this r. If r is positive, then you choose the upper side. So Jordan lemma is the proof. I gave that statement. Had there been a minus sign, then you should have closed from the bottom. Okay, please look at the complex integration. At least this course, you should be able to do all the Green's function and complex integration and some statistical field theory. Okay, some Feynman diagrams, you should be able to do it yourself. Well, some quantum field theory too. I mean, these are not difficult. This is commutation relation, anti-commutation relation. Okay, so this is part A. And let's look at part B. So these are all revision. Huh? So problem solving. So Green's functional or Schrodinger equation. Okay, classical field. I'm not wanting quantum. So we in fact we just did some of it. I bar d by dt plus Laplacian Green function okay, so this is that equation. So the interesting thing is this equation is very similar to diffusion equation, except the I. If you get rid of I and h bar, then it's a diffusion equation. Okay, this becomes a minus sign. Okay, so so the solution is very simple. I mean, solution is also very similar. You just need to keep I. So in the Fourier space, we write this as g of k omega, g of k omega, right? So this is a g of rt, right? Fourier space, e to the power I k dot r minus I omega t dk d omega. So this is my conversion GRT, and we write this is 1 by 2 pi q. Or in you can write to d dimension, d real space dimension is d. So if I substitute that, I'll get minus I h bar omega minus h bar square k square. So sorry, minus minus becomes this is a, so I will come. If I take the time derivative, what will I get? So we should do it carefully, okay? So I h bar and minus I omega, right? So this will give minus I omega, time derivative. And Laplacian of this one will give ik and ik, so that is minus over 2m g of k omega, and right hand side will be I h bar. So this is written as integral ik dot r. So delta function is 2 pi, so dk by 2 pi d omega by 2 pi. So whether I need to write 2 pi for here also. So this part is common in both sides, the exponential also. So if I do the integral of this one with dk or d omega, I'll get 1 times I h bar. Okay, so this is I did in the class before. So gk omega is I h bar gets cancelled. So this is going. So you write this as I h bar times I h bar. So I h bar is going away from both sides, this side. So I'll get minus I omega plus I h bar k squared by 2m. Okay. So this is my Green's function. So what is the Green's function for diffusion equation? Other than I, pretty much the same. So let's write down for that one. d by dt of minus Laplacian, kappa Laplacian, okay? Diffusion equation is d by dt of psi equal to kappa grad square psi. So this is GRT is delta R delta. So this will give me minus I omega, and minus minus becomes kappa k squared. G equal to. So this minus I omega is the same, but here this I extra I sitting there, okay? So kappa is replaced by I h bar by 2m. Okay, so that's the only difference. So you replace kappa by I h bar square 2m and same solution. Okay, bit of hand waving called analytical continuation, because the integral plane will be going in some different directions, but it is the same. Okay, so we did this integral. So first do the d omega integral. So this in k omega, then you have to go to real space. So first you go to time, then space. Okay, in fact you can do in d dimension, but I asked you to do in 3D, right? Well, I didn't say that. So d dimension is a bit complicated, but 3D you can do, okay? So I will accept 3D. I did in the class for 3D. Or make the connection with d dimension. I had to go a lot of pages back to get the answer. Okay, so just, well, is there in the notes? I have shared the notes before the exam. So it is 2 pi I h bar tau by m minus d by 2 summation I m r squared by 2. Okay, and it works. I h bar by 2m. If I replace by kappa is replaced by that, it works. Okay, so that's the answer. So even I mean, if you just wrote the answer by analogy, I'm happy. You should derive it. Okay, this is a 10-mark point, so you should derive it at least for diffusion equation or for this. So do the do omega integral, then the space integral for 3D. It's also possible to do in d dimension, but it's more complicated. That integral is not straightforward for general dimension. In my notes, I given that the derivation. I think, I'm not sure. So this book by Physical Mathematics, that book has the derivation for d dimensions. Okay. So this is our Schrodinger equation Green's function. I'm assuming this to be the classical field psi, and this is exactly same as path integral. Okay, path integral gives you the same answer because it's the same thing. Okay, you can do using path integral or using this. There's another book I can recommend called Greiner. Heard of this guy, Greiner? So Greiner has written lots of books. In fact, he's like I think he wanted to do something like what Landau did. So he has book on classical mechanics, electromagnetism. So there's a book on QED where he does all these Green's functions from scratch. Okay, and he also relates this to what is that? There is a theory, this is that each point acts like a source, and what is that thing called? Wave propagation, Huygens principles. Huygens principles, in fact, that's, I wanted to look for it, so I recently discovered he makes a connection. So, final path integral is something similar to the Huygens principle. It is spelling the paths, and so you get contribution from different paths. So, it is a similar connection. Okay, so the last problem. So I'm not going to do that derivation, was done in the class. Since we have recording, I think I should probably do it, but well, I mean, okay, maybe this I'm not sure I did in my NPTEL lecture. So let me say, so the idea is to do the d omega integral. So this one will be d omega integral, okay? No, this is RT, this is RT. So first you do the time integral, so that will d omega by 2 pi minus omega I by t squared 2m. So this is the e to the power minus I omega t. Okay, so where are my poles? So my pole is so you can so I'm doing the omega integral. So so you can get rid of, bring the I outside. So this is d omega, no? So there's another thing, the minus I omega sitting there. So I can multiply by minus I, both plus I top and bottom. So this becomes I squared is minus 1, so that becomes this, plus, so this I times I will be minus h bar k squared by 2m. So denominator becomes that, right? Because I just multiply by I and I want to bring it the same. So my variable is omega, so I should have omega there. Okay, so well, just get rid of this minus I. So my pole is sitting here. Pole is sitting on the same line as line of integration. So what should I do? I shift the pole up or down. Okay, we've done the trick. So if it's a propagating outward wave, then you shift the pole one direction. So you've done the trick before. So I don't remember right now, but you shift the pole. And then do this closed integral and pick the contribution. So this will give me a contribution from this pole. The pole is inside the contour now. And okay, so for the, I did this derivation for the diffusion equation. So that integral 3D d omega part. Yeah, so that gives us pole is shifted and then that gives me this for that one. Diffusion equation. Okay, so d omega integral gives me, if I shift it for the diffusion, it gives me minus nu k square tau. So nu is replaced by what? I said nu is replaced by IH bar. So this is replaced by, so nu has to be replaced by, just make the connection, IH bar by 2m. So this is replaced by IH bar by 2m. It turns out for the diffusion equation, the poles are here and there on the imaginary line. But it turns out the poles for Schrodinger equation is on that line because of the I is creates a thing, but still it's okay to shift things up. And this is my Green's function gk tau. Now I do the space integral from k to x. Yeah.
So I'm done this thing by the theorem which I did. Is it right?
What theorem?
There's a theorem which makes it easy to solve. And whenever ऐसे नहीं किया मतलब safety वाली प्रॉब्लम नहीं किया मैंने theorem से किया.
I see. Okay, I need to check which theorem. Which theorem are you applying?
There is no proper name for it, but there is a theorem.
Oh no, this theorem should have proper name. Okay, so I need to check what you did. So this is a shifting will give you this, okay? Because that pole is inside and it will give that. Now I need to go to real space after this. So that will be g of RT. Let's write that. G of RT is integral e to the power minus h bar k squared by 2m minus k squared I do ik dot d of k. Now this integral is done by what? So this is looks like Gaussian. So you convert it to Gaussian. So this k squared, this k, so I get r squared. I'll get r squared from that. You get my point? So I get alpha k squared plus k. So I add and multiply, add and subtract. So there will be r squared come from here. So I just add and subtract, and then really minus r squared will come outside. So you convert it to Gaussian, and Gaussian integral dk will give you square root 2 pi. Yeah, so the d-dimensional Gaussian will give you 2 pi to power d.
Okay, it will involve the
Surface, yeah. So that's the trick. That's a physical mathematics. That's what is done there. So you can convert this to d-dimensional integral. So you keep this k vector, and that gives you that. So that's not straightforward, but it's doable, and that's why I get is 2 pi to the power d. In fact, you recall in our integration, in d-dimensional integration, statistical field theory, okay, dk1, dk2, dk3. Remember that one? So I write it as a matrix. So by the way, if you learn something, don't let it go. So this we write it as a matrix. So the k dot r is not a kr. It is kx, x, ky, y, ky. So this you write it as a matrix. So the integration formula which is used in statistical field theory should be applied there, and that is why you get 2 pi to power d. I have not done this one, but maybe I'll do it, and I should be able to get the answer. So diagonalize the matrix, okay? That's what we did. Diagonalize it, and that gives me A transpose A inverse, and so on. Okay, so that is the derivation. Now the last one, the Feynman path integral, Feynman propagator. For a scalar field. Okay, so this was partly done in the class, not all of it. Okay, so if you did what was done in the class, that should be okay. This is slightly dangerous, huh? No, don't do anything, otherwise it will bite you. Okay, so it is so it's getting warm, no? So you want the fan to be turned on, or it's okay? Well, we have 10 minutes, 5 minutes. Okay, that's so. I will let me just sketch. I have to go very far to the right. Okay, fine propagator. Okay. So how is it defined? So g of xy is a Green's function, in fact. For so we do it for vacuum. Okay. Time ordered product of phi of x, phi dagger, phi operator, phi creation operator. So these are operators. Okay. So it's a time ordered product. So if x is so if y is after x, so it is written as theta. So it is a 4 vector, huh? So x has time and space. So y0 minus x0. So if y is after x, so 0 phi dagger y phi x 0 plus theta. If x is after y, so 0 phi x phi dagger y. And all these are operators, okay? So these are operators. So we have to compute for both of them. So let's look at, so this phi, so you need to do phi x acting on 0. So first let's write down what is phi x. The complex scalar field, so phi x is written as dqp by 2 pi cube 1 by square root 2 ep a dagger, no, ap e to power minus I p dot y plus bp dagger. So this is a destruction operator, so it destructs at p and creates an antiparticle. Antiparticle will be phi fx b dagger p e to power I p dot x. So this x. Okay, so is that understandable? So it's a destruction operator. So it destroys the particle or creates an antiparticle. Okay, so both are to be included for scalar field. So this I did in the class in some detail. I hope you got that derivation right. So this one, this one is integral dqp by 2 pi q. So because I need to create a particle at y and destroy at x. So sorry, here create a particle, destroy a particle at x, which is here, and create a particle at y. Y is later. Okay, so that is the first. No, actually, wait. Well, the one I'm writing here is this one. The one I'm writing is create a particle at y and destroy at x. So in forward motion, so first you have to create a particle, then destroy, right? That's a real causality. So is written as create a particle at y, this is the time axis, and destroy at x. So time forward, so it is created here, goes there and get destroyed. So in some process, it happens. So you may have one virtual particle created at y and destroyed at x. So this one is written as dqp by 2 pi q 1 by 2 ep e to power ip minus ip x minus y, and okay, where is that stuff? Okay, and theta. So this is that part, and I need to put theta in front. Theta x0 minus y0. So this is the this term. The second term is called advanced Green's function. So first create and destroy later. Or you can create something here, destroy something, then create. Or it's like antiparticle is created and antiparticle is destroyed. You should think of antiparticle creation. Okay? So we did that before. Okay, so please keep in mind a particle destruction is same as particle going forward in time is same as antiparticle going backward in time. Okay, so this is that Feynman integration, Feynman interpretation. And the second one is this one is integral. So this theta is coming here, and so this integral is the same, and this part is e to power I p x minus y. So the sign change. There's a minus ip here, there's plus ip there, and the theta is also different. So this is theta. Flip off the time coordinates, and you get this change. Okay. Now I need to add them together. So the total is the sum of the two, right? So what do I do when I add them? So the theta I'd like to write in terms of some integral. I don't know how many of you tried this problem. How many of you tried this problem? Good. Okay. So this theta we need to write in terms of some integral and merge the two integrals. So theta is a time integral. So theta x0 minus y0. So in fact I told you step function can be written as a Fourier transform. One problem in last right. So I dz by 2 pi e to the power minus iz x0 minus y0. So Fourier transform of this is that, right? I wrote in the stuff. In my objective question had this problem. What is the Fourier transform of this? It is there. Okay, so it is basically the same stuff. So now I substitute it here. Now I have a z integral and p integral. So this is the momentum integral, and this is like a time integration. You see what connects with z with time? It is energy, Et. No, invariant quantity is Et minus p dot x. So energy, time, and momentum space. So these two integrals are this one and that one is combined. So that's what Feynman did. Okay, so these two are combined. So you multiply that with this, and with a sign change, so y0 minus x0 comes there, and you multiply with this. So is there in our reference book, gifted amateur book. So you can do that stuff, then add them. This part I did not do in the class, and I will give you credit if you just go this far. So multiply this one with this and flip one with that and sum up. So it turns out when you sum it up, I write down the last step. D4P. This is a bit of algebra. By 4 for IP. Okay. Okay, so this is that Green's function. And this is the full momentum. So E, it has 4 components: E x0 minus y0 minus P dot x1. Okay, so if you go that far, you are okay. Now this can also be simplified. I think this can be written as P square minus M square. Okay, so in fact that's easy to see. EP squared is P squared plus M squared, right? Energy is, it's an Einstein relation. E squared minus P squared is M squared. Okay, so if you substitute it there, I get P0 squared minus P squared minus M squared plus I epsilon. I'm plugging it here. So this is like energy squared minus P squared. So that is the new, this is 4 momentum, this is energy and momentum, so this is P squared. Well, I should write a one thing. This is P vector, okay? This P vector dot P vector. So this whole thing is called P squared. So what is P squared? P squared is energy squared minus momentum squared. So I'm just rewriting this stuff. Is energy squared minus EP squared is energy squared minus momentum squared minus M squared, which is that. Okay, anyway, so this was just to